Stay a while and listen.
Arginine reduces signs of Alzheimer's in mice. It may be more accessible than other treatment options. December 2, 2025. Share. Application of the amino acid arginine decreased amyloid beta in the eyes of fruit flies and the brains of mice engineered to express this misfolded protein. The cognitive abilities of the mice, including memory and anxiety behaviors, were also improved. While arginine did not outperform the green tea extract EGCG, that extract has less bioavailability and more toxicity. In a new study, the amino acid arginine shows promise in animal models of amyloid aggregation due to its ability to promote protein folding. The researchers suggest that it could be useful for early prevention and treatment of Alzheimer's. 1. Hold it and fold it. Amino acids, the building blocks of proteins, can be potent bioactive molecules in their own right. Arginine, an amino acid abundant in foods like pumpkin and meat, has been shown to act as a chaperone, a molecule that assists in protein folding, 2, and is already used to treat several diseases. In this study, published in Neurochemistry International, researchers from Kindai University in Japan and partner institutions attempted to use this quality of arginine to tackle Alzheimer's disease. While scientists still don't fully understand the etiology of Alzheimer's, protein misfolding definitely plays a big role. 3. Misfolded amyloid beta, A-beta, protein forms fibrils and then plaques, which are Alzheimer's most iconic hallmark, although the role of soluble A-beta may be even greater. Chaperones can sometimes inhibit misfolding of aggregation-prone proteins. 4. Preventing fibril formation. First, the researchers incubated synthetic A-beta-42 peptide, the 42 amino acid form of amyloid beta that is especially prone to aggregation, and monitored aggregation in vitro. As a positive control, they used epigallocatechin gallate, EGCG, a green tea polyphenol known to prevent amyloid aggregation. 5. Adding arginine reduced the fibril formation signal in a concentration-dependent way, up to roughly 80% inhibition at 1 mm arginine. Transmission electron microscopy, TEM, showed shorter, less developed fibrils. Interestingly, EGCG, a gold standard amyloid inhibitor in vitro, was more potent than arginine. The authors, however, did not take EGCG into their fly or mouse experiments, possibly because its profile is already well explored and less drug-like. EGCG has poor oral bioavailability, binds promiscuously to many proteins, is slow to cross the blood-brain barrier, and has shown liver toxicity at therapeutic doses. Fruit flies with human A-beta. The researchers then experimented with Drosophila flies genetically modified to express human A-beta-42 in the eye, a standard neurodegeneration model. Arginine reduced the fraction of cells with A-beta aggregates in a dose-dependent manner. The authors reported no change in A-beta transgene expression, meaning that arginine affected aggregation/clearance, not production. A-beta toxicity, which in this model manifests in eye shrinkage, was reduced as well. Our study demonstrates that arginine can suppress A-beta aggregation both in vitro and in vivo, explained Professor Yoshitaka Nagai, a senior author. What makes this finding exciting is that arginine is already known to be clinically safe and inexpensive, making it a highly promising candidate for repositioning as a therapeutic option for AD. Fewer dense plaques in mice. Finally, the researchers moved to a mouse model, which carries 3 amyloid precursor protein, AP, mutations and is used to mimic A-beta-42 plaque deposition starting around 3 to 4 months. These mice also develop behavioral abnormalities. Mice received 6% arginine in drinking water starting at 5 weeks of age. This translates to a human equivalent of 940 mg per kilogram per day, about twice the maximum oral arginine dose currently approved in Japan for urea cycle disorders. At 6 months, mid-stage, immunohistochemistry for A-beta showed a clear reduction in plaque area and number in the cortex and hippocampus compared to controls. However, at 9 months, near saturation of plaque load, the effect was weaker, with only a non-significant trend toward reduced plaque area in the hippocampus, likely because deposition was already near the ceiling. Notably, arginine-treated mice had fewer dense core plaques than controls at both 6 and 9 months. Insoluble A-beta-42 was significantly reduced by arginine at 6 months, while soluble A-beta-42 was unchanged. Like with the flies, AP mRNA expression was unchanged, again arguing for an aggregation/clearance effect rather than changes in AP production. The researchers then tested the mice's cognitive abilities. In the Y-maze test, which assesses memory and anxiety via spontaneous alternation and locomotor activity, arginine significantly improved results at 9 months. At 6 months, however, only a weak trend toward improvement was observed, which somewhat contradicts the A-beta accumulation results. Variability between individual mice was high, which the authors note as a possible reason for inconsistent behavioral results. However, it is also possible that the level of dense plaques, which was lower at 9 months than at 6 months, played a decisive role. A-beta-42 accumulation drives neuroinflammation, so the researchers measured mRNA levels of the pro-inflammatory cytokines IL-1 beta, IL-6, and TNF-alpha in the cortex. These were all significantly reduced in treated mice compared to controls. A candidate for early prevention. The authors concluded that arginine behaves as a disease-modifying candidate that targets A-beta aggregation rather than just symptoms, with the benefit of being orally available, relatively cheap, and already clinically used for other indications. Because A-beta pathology begins 15 to 20 years before Alzheimer's symptoms, they see arginine as particularly suited to long-term, preventive, or early-stage use, in contrast to expensive intravenous antibodies. Our findings open up new possibilities for developing arginine-based strategies for neurodegenerative diseases caused by protein misfolding and aggregation, noted Nagai. Given its excellent safety profile and low cost, arginine could be rapidly translated to clinical trials for Alzheimer's and potentially other related disorders.